Sir?
Yes.
Can we please go back
very
to...
fast in the last part.
Yeah?
Yeah, of course, we're still digressing that last section where you are saying that those polynomials equal to 0 and then the writing is not very clear, so we're trying to follow.
Sir, can I please ask, why did you equate this specifically to 0?
Well, you told me that you gave me this line from linear dependence, right?
Mm-hmm. But why isn't it equal to A or C or like whatever other thing? Why is it specifically equal to 0?
Wait, what you are thinking, what you are saying. You told me that this list is linearly dependent.
What?
So there exists certain scalars. What does the linear dependency mean?
Oh,
There will exist certain scalars whose linear combination will be equal to 0, which is exactly this line.
Okay.
Now recall the definition of addition and so on and so forth in this form VB. This is a linear transformation. This evaluated at V is exactly the stop line. Yes?
Yes, sir.
So therefore, this stop line is actually saying that this linear transformation at V is 0. Okay? Now I made a simplification. I said that let me consider this polynomial. Same coefficient. Okay? That function, I'm taking that function, it's a polynomial function. And we saw that if I take a polynomial function, replacing that x by f gives me another linear transformation, which was already denoted by PF, right? So PF, so this sentence, which I wrote, you agree, is the same thing as saying the linear transformation PF at G is 0.
Oh, is this V?
Okay?
Yes, sir.
But then this means that V is in the kernel of this linear transformation PF.
Yes.
That's what I wrote.
Thank you, sir.
Okay? Alright. Now, we need some facts from algebra. Basic algebra. Like our Rx, we can define this set of polynomials whose coefficients are complex numbers instead of real numbers. Okay? So these are polynomials okay? So for instance, Ix minus 3, that's a complex polynomial. Ix squared plus 3 minus 4ix plus 5 plus 6i. That's also okay? So these are just the addition and multiplication, everything is as same as we were doing, but the coefficients are just now complex numbers. Okay? Nothing more. Clear? Good. Now, this is one of the most celebrated theorems of mathematics. It is called the fundamental theorem of algebra. It's a statement is so simple, but its consequences are huge. Okay? Now what does it say? It says if, remember, what is the root of a polynomial? If you can find the value of x such that the polynomial vanishes, is equal to 0, right? It says every polynomial with complex coefficients has a complex root. That means, in other words, given any polynomial with complex coefficients, there exists a complex number such that so this is going to happen. Always. This is not nice. Yeah? There exists one such. But let's see immediately what happens. So, a polynomial of degree n has exactly n complex roots. Okay, why? Let's see quickly. That's very quick. Yes.
Can I please ask what exactly is a complex root?
Complex roots with n complex numbers which satisfy like this. Alpha is a complex.
Sorry.
So such an alpha is often called a complex root. Okay? This number alpha, such that P of alpha is 0, is a root, but since it is a complex number also, we shorten it by saying it's a complex root of P. Okay? Clear?
Yes, sir.
Now, let's see. Suppose you tell me that Px is a polynomial. Now you know how to divide this by, saying sum x minus alpha, right? You know that we're going to, yeah? So,
Sir, could you please write just a teeny weeny bit lower?
So if I give you any polynomial, you know that, so given any polynomial, there exists a unique polynomial Qx such that degree of Qx is equal to degree of px minus 1 and the unique right? This is just the division algorithm which you did in school, right? You have a polynomial, you divide by x minus alpha, you know how to do it, yeah? So that same thing, so it tells you that this is the quotient and this is the divide, this is the remainder, right? So alpha is a root of px. This means that p alpha is 0, and which means that, same thing as saying, the remainder is 0. Right? That is when you say that alpha is a root. Okay? Now, so suppose, what did you tell me? You started off with px. You told me that alpha 1, it has a root. I am saying that the degree of px is n. Okay? You told me that alpha 1 is a root. So it looks like x minus alpha 1 times qx. So the degree of q is 1. Okay? So, the degree of q is 1 less, which is n minus 1. Yeah? But it also has complex coefficients. So, by that same thing, it has a complex root. So, if you tell me that q alpha 2 is a root of qx, then p of alpha 2 is 0. So, every root of qx is also a root of px. So, it can be written as right? But the degree of q2 is n minus 2. So you carry on doing this in n steps. In n steps. And you are going to get a constant. Where gamma, the degree of gamma is 0, right? That means it's a constant. So, it turns out, in the end, that px will be 0 even only if and gamma is non-zero. So, even only if x is either alpha 1 or alpha 2 or alpha n, that means alpha 2, alpha n are all the roots of px. Okay? So, this is saying that every polynomial has a complex root actually means that a polynomial of degree n has exactly n roots. Okay? So what does it mean? It means that if you try to draw the graph, then exactly n times it will vanish. It will sit on the complex plane. The rest of the time it is above or below. Okay? So there is only n different places where it sits on that complex plane. Yeah? So it is exactly n different roots. Okay. The second one says, if px has real coefficients, every real number is a complex number also. So by this, it has a root. Okay? P alpha is 0, that means alpha is a root. Then it tells me its conjugate is also a root. Okay? Well, it's very simple. Suppose Px, let's take an example. This any example can be extended. Suppose Px is a quadrant. Say 2 plus 3x plus 4x squared. Okay? You are telling me alpha is P alpha is 0. So 2 plus 3 alpha plus 4 alpha squared is 0. Okay? Now take the conjugate of this. Remember, 2 plus 3 alpha plus 4 alpha squared. The conjugates of reals are reals themselves. So the conjugate of 2 plus 3 alpha plus 4 alpha squared is again 2 plus 3 alpha bar plus 4 alpha bar squared. Okay? And the conjugate of 0 is still 0. So alpha bar self-satisfying. So what does this say? It says that polynomials with real coefficients have conjugate pairs. Roots are in conjugate pairs. So if a plus ib is a root, then a minus ib is a root also. So what does it say? And hence, every polynomial with real coefficients, degree of Px being odd, has a real root. Right? The degree of Px is n. Corollary 1 says it is n roots. Okay? Now we have taken Px to be a polynomial whose coefficients are real. So these n roots, they come in pairs, in conjugate pairs. Okay? So pair. Okay? So if it is odd, then how many pairs are there? One person, one will be left out, right? So it is its own conjugate. So it means that it's real. Okay? So every polynomial with odd coefficients, with real coefficients and degree odd has a real root. What happens to even degree ones? Good. Again, pair them off. So observe, and if even, then it is a product of linear and quadratic terms. Why? So, some of the roots are reals, throw them out. The ones which are complex, they come in conjugate pairs. So let's see. So the roots look like this. So if there is alpha, then this conjugate pair. Okay? What is the product of this? This is x squared okay? But remember, this is x squared. This becomes 2 times the real part of alpha, and this becomes the modulus of alpha squared. Okay? Not sure. Okay. Alpha, say, is a plus ib. Alpha bar is a minus ib. So alpha plus alpha bar is 2 times a, which is the real part of the alpha. Right? And alpha bar is a squared plus b squared. right? So that's the conjugate, that's the modulus, okay? So you see, so it is something like this. This is now, this one is real, this one is real, so this is a real polynomial, but it cannot be broken up, as it doesn't have any real roots anymore. So it's something like x squared plus x plus 1, okay? So any polynomial of odd degree has a real root, of even degree either they have real roots or it is a product of linear degree 1 terms and degree 2 terms, okay? No degree 3 or degree 4, okay? That's one of the main reasons, for instance, this is one of the main reasons, for instance, you do partial fractions, remember in integration, you do partial fractions, the denominator only has degree 2. You don't go to degree 3. Because the moment you go to degree 3, it has a real root. So it factors out. Okay? So things are either degree 1 or degree 2, which doesn't factor anymore. This is all the problem about real polynomials. Okay? So now, let's come back to our original problem. So where were we? We said that we started off with this S.
Sir.
Yes.
Okay.
Sir, since we have a technical error, can you during the day send us the memo for the self-assessment, please?
Memo for?
Of the self-assessment at least, so that at least we can have a clue.
No, there will be no memo. There is no memo. I will actually make sure that this video actually gets to you without this technical error.
Can I just
okay.
Okay. So we took this polynomial from that. No, it's from this level now. This you should be able to see.
Yes, so we can see it now.
So I'm just rewriting what we came with. Okay? So that's where we came. Now let us look into this polynomial. Using this fundamental theorem, I know that there are complex roots of this. Okay? There are complex roots. And this polynomial, this one factors. So it could be that there is no degree 1 polynomial. For instance, x squared plus x plus 1. It's a 2-degree polynomial. It doesn't ever factor as a product of 2.
Again?
2 polynomials of degree 1. Okay? Or there could be degree 1. There could be, so x squared minus x squared plus 2x plus 1. It is x plus 1 times x plus 1. Right? But x squared plus x plus 1 never factors as a product of 2 linear polynomials in R. That's the most important thing. Okay? So, for example, this is actually x plus and so actually you can write it completely. Right? So, right? It never factors as a product of polynomials of degree 1 with coefficients in R. It does so with coefficients in complex. These are complex numbers. Yeah? But not in R. It doesn't. It cannot. So, that is what I'm trying to say. For polynomials with real coefficients, either you will have a real root, that means you will have a factor of degree 1 in R, x, or you will have it as a factor, you will have a second degree polynomial which is no more factorizable. Okay? So second degree polynomials which do not have any more linear factors in Rx are called irreducible. As if reducible means you are breaking it. Irreducible means something which you cannot break. Okay? So you cannot. So the irreducible polynomials with real coefficients are either linear ones, that means ones which have degree 1, or degree 2. Okay? There? So, Px factors as a product of degree 1 or degree 2 polynomials. Okay? So in particular,
excuse me, sir.
yes,
I'm slightly confused there about your factorization. Is it supposed to be root 3 over 2 or should be root 3 over 3? I'm not sure.
this is 4.
Okay, not 9. Okay, thank you.
9. If it is 9, this doesn't match, right? This is x squared plus x plus 1/4 plus something. So it has to be 3/4. Okay. So, I can write Px as a product of Qx and Rx, where Qx is no more reducible. Okay? That means its degree is either 1 or 2. That's the whole story. Okay? But then, since, remember, so therefore, Remember, the multiplication changes to composition. Yeah? Okay. And hence, since you told me that QF is no more reducible,
That concept.
there cannot be anything which vanishes over there, and thus okay? So, this therefore tells us that, one minute. Sorry. I cannot. 1 minute. I was wrong. Okay? And this tells me, remember this degree is 1 or 2. So this tells me that how am I saying so? You have to slide something like this. And therefore, FP. Okay? So that's how I will get hold of this program. Okay? So there always exists real an eigenvalue of linear transformation. The question is, how do I compute it? Okay? The computation comes so how to compute? So, let A be its matrix. You want V not equal to 0 such that if V is equal to lambda V. That means you want a solution where x is not equal to 0. This means that you want to have a solution of this homogeneous system of linear equations, which always has a solution, I know. Okay? So, and x that means you are forcing the determinant to be 0. That means this matrix, even before, so since it has a non-trivial solution, you are forcing is not invertible, and this is forcing determinant of A minus lambda I is 0. Okay? So, how do you compute it? Look into its corresponding matrix and go on to find the determinant of this. This will be, so remember, determinant of this is a polynomial. Okay? So if I write it like this is a polynomial in lambda of degree equal to the order of A, which is equal to the dimension of B. Okay? So, it's a real polynomial. You know that every real polynomial can be factored as a product of linear or quadratic ones. From there, you know that it has a eigenvalue. Okay? Clear? So that's how you often find the eigenvalue of linear transformation. And I told you how to find the eigenspace. Okay? And I'm left with two more facts, but I think I'll do it next time. And I'll speak more on diagonalization next time. So I'll speak about that and the linear dependence and so on of eigenvalues or eigenvectors. Okay? So let's stop unless you have questions.
Yes, sir, we have questions.
1 minute. 1 minute.
We do have questions, sir.
1 minute. What I will do is, I will actually make a separate, because today's class was completely in pandemonium. So I'll make a separate video. Unfortunately, it will not have your nice inputs, but it will be a video which I will make from home, and as a single file I shall upload this separately onto that same website. Okay? So at least you will have this whole material without any pandemonium for your reference. Okay. Now questions.
No question.
Okay, so there's a question. Show that if r to the power of f and the function goes to R2 be a linear transformation that the curve function f is equals to, in brackets, x1, x2, x3, x4, and the element belongs to r to the power of 4.
1 minute. What is it? Again, r to the power?
R to the power, show that if r to the power of 4, the function goes to r to the power of 2, be a linear transformation such that the curve function is equal to x1 in brackets.
Which one is equal to?
X1 of f.
The kernel of f.
The kernel of f
is equal to x1, x2, x3, x4.
Is an element.
Yes.
Elements to the r to the power of 4.
Yes.
And then semicolon, x1 is equal to 5, x2, and x3 is equal to 7, x4. Then the function is a surjective.
x1 is equal to 5.
Yes.
Then F is surjective.
5x2. x1 is equal to 5x2.
Oh, 5x2, okay.
And x3 is equal to 7x4.
Okay.
Then F is a surjective.
Well, this is quite simple because what you are telling, the members of the image is to be the kernel. If this is coming from kernel of F, then this is actually equal to right?
Right?
Clear?
Yeah?
Yes, clear.
So this is equal to sorry. Clear?
So you're saying that x2 is equal to 5, 0, 1, or 1?
No, I didn't say any. I said that this vector is a sum of these two vectors. Right?
Okay.
x2 times this is 5x2, x2, 0, 0. x4 times this is 0, 0, 7, x4, x4. And that's the sum is this. Right?
So,
Right?
so in x2, it's 5. The factors inside are 5.
Look into this.
Oh.
From here I can write this.
Okay.
Then it is this. Right?
Right?
So and it is clear that this so. Obviously, that's what you told me. Writing all of this is saying this is the span. Okay? And if you look into these two, this list is a linearly independent list. Right? So, the dimension of kernel is 2. So, the dimension of the image is R2. The codomain is R2. So, therefore, the image done. See the power of that small little statement. Dimension of the kernel plus the dimension of the image is equal to the dimension of the domain. See the power of that. You don't need to calculate. It is just this much.
So we were talking about dimension when we were talking about that, sir.
When you're talking about?
When we're talking about R4, the function going to R2, it's a dimension.
Yes, because it's a linear transformation. The image will be a subspace. And the dimension of the image, therefore, will be either 0, 1 or 2. Okay?
Okay.
If it is 0, I know there is only one vector subspace of any vector space of dimension 0. That is a trivial, containing only 0. R2 has exactly one subspace of dimension 2. It is itself. And all others are of dimension 1. Okay? It turned out that the dimension of the image is 2. So, it must be R2. Image is a subspace. See what I am saying? Image is a subspace, its dimension is 2, and there is only one subspace of dimension 2 of R2, which is R2 itself. So, image of F must be R.
So can I please ask, is this by the invertible matrix theorem?
What is it?
It's not, no?
What is it?
Is it by the invertible matrix theorem?
I don't know what is the invertible matrix theorem.
It says that if something is linearly independent, then the image will also span the vector space.
If again.
It says that if something is linearly independent, then it will span a subspace, a vector space.
Yes. So what is the invertibility and so on, I don't know. But if something, that's what, every subspace has a basis. So how to find it? I have shown that the kernel of F is spanned by these two vectors. And I can immediately see that these two vectors are linearly independent. Okay? These two vectors are linearly independent. Why?
Yes, sir.
So, it's a linearly independent span, so this must be a basis for kernel of F. And hence the kernel of F has dimension 2.
So how did you know that it spans kernel F?
Because you told me by these relations that a member of kernel of F exactly looks like this.
Oh. Okay, sir.
Okay? Next. Yes.
I understand you're currently going through load shedding where you are.
Yes.
So does that mean that Thursday's lecture will be moved because there's load shedding at the same time as our lecture then as well?
I don't have the schedule. In fact, I don't know. The schedule for today didn't tell me that there would be load shedding. Okay, there is load shedding now. And I will not be able to predict whether there will be load shedding next Thursday.
Well, in 2 days' time we have a lecture scheduled from 3 to 6 and load shedding is meant to happen from 4 to 8:30.
No, today's lecture schedule was from 4 to 7.
That's next week.
Today.
Yeah, today is 4 to 7.
Yes, and next week is also 4 to 7?
But Thursday the 21st, the public holiday, you've got a lecture scheduled from 3 to 6.
Yes. But you're right, but I don't think we'll be able to meet on a public holiday.
Okay.
Yeah.
Sir?
Yes?
In Pretoria, we missed about 3 classes because of strike, and we noticed that the videos are not uploaded.
Videos are uploaded up to lecture 5, but there was a mistake. The lecture 4 seems to have been repeated in some of the ones for lecture 5, so it has to be redone, and well, it will take some time because of this load shedding over here. People cannot actually do it. So I really don't know, and things are made difficult by the system over here because it doesn't get recorded into a very familiar file format. So it has to be re-encoded again. So nothing to be done. You have to wait for a little while before you get those.
But assignment is due, sir.
Yes, I understand. Can you please send your queries directly to me? Then I can try and answer them. Because, or ask me the questions here so that...
Okay, sir. The question is, given a finite dimensional vector space V and a linear transformation, and V, like F and G, go from the domain V to the codomain V again, show that G of F is bijective.
Which one is that
If
one?
and only... But what are we jumping?
Oh, what no jump fish?
Let's come with our region, guys.
What is it? What is it?
No.
Okay, something which I shouldn't listen. Okay. So what is G composed F is bijective?
Oh yes, G composed F is bijective. I'm sorry, I lost my pen. If and only if both F and G are bijective.
Yes.
Let Rx, like, you know the polynomial x that we use, go from, okay, so we have F and G goes from Rx to Rx, like the code from domain Rx to codomain Rx, be the linear function such that...
Which one is this?
Excuse
Which
me,
problem
sir?
is this? Do you have the problem with you?
Yes, sir.
Okay, 1 minute. Is this problem 4D?
Yes, sir.
Yes, okay. So, you have a finite dimensional vector space. And you have to show that you have two statements. G and F are both bijective. And B, G composed F is bijective. Obviously, if G and F are both bijective, then the composite is bijective. There is nothing to worry about, right? It's a basic set theoretic fact which we used. The real part is this one. Okay? Now, this is bijective. Implies that F is injective and G is surjective. This holds for any function of space. This was one of the problems in the self-assessments, or you try to prove this. Okay? And using, in fact, one of the problems in, I think in the, remember it was shown that F is injective if and only if F is left cancelable, if and only if F has a left inverse, and so on and so forth. Okay? Using all of that, you should be able to show this. Okay? Now, once you show this, so what do you have? You have assumed G composed F is bijective. From there, you know that F is injective and G is surjective. You are given that this is finite dimensional. So let B say its dimension is okay? Now F is injective. So that means if you look into this, what happens to F? Well, it will take you something, but these are all distinct, right? Because F is injective. Okay? You cannot have B1 here, or you cannot have a repetition in this place. Okay? So the n things come in a different order over here. Okay? So it's injective. Now, therefore, whatever member that you might take from here, there are n things. N places n things. So it's obviously F is surjective also on this little set of B1, B2, Bn. Okay? So if it is surjective, it means that for each K, there is a unique P such that F of Bp is also Bk. Okay? So therefore, every linear combination of the Bk's can be written as an image.
Sorry, sir.
Yeah.
Can you please rewrite the last statement somewhere above there? Because
Okay. I'm giving you a special case for n equals to 3, say, and then you should be able to do it. So suppose, or let's say n equals to 4. You told me that F is injective. So over here you will have all the 4 things. F of B1 will be something. F of B2 will be something. But whatever you might have, they are not same. None of them can be equal, right? Because you told me that F is injective. Okay? Now if you take, say, A times V1 plus, say, B times V2 plus C times V3 plus D times V4. Well, this is nothing as A times F V1, B times F V4. By linearity, this is A times A V1 plus D times V4. Okay? One minute. So anything becomes actually a span. Alright? Seen in other words, since F is injective, its kernel has dimension 0. So its range has dimension same as n. Okay? On the other hand, since G is surjective, then G has image dimension n and kernel 0. Kernel's dimension 0. Therefore, both F and G are bijective. That's it. So it's again an application of the dimension rank plus nullity theorem. Okay? So it's again an application of rank plus nullity theorem modulo this observation about functions, which is something you must do for yourself. It's something very, very simple. Okay? So once you do that, the rest is, you have told me that F is injective, so dimension of its kernel is 0, so dimension of its image is same as the dimension of V, so therefore F is surjective. G is surjective, so dimension of its image is same as dimension of V. Therefore, the kernel of G has dimension 0, so G is injective. So F is both injective and surjective, so bijective. G is both injective and surjective, so bijective. Done. Okay?
Can you please zoom out what you just wrote? The
Zoom
B1,
out.
B2. Yeah, can you bring the camera closer?
Well, this is written on paper. I cannot zoom it. I don't know how to zoom it in.
So we can't see the last part.
Okay. Let me say it again. Suppose you get this, what I have written in this circle. Okay? Now, you have told me therefore that F is injective. F is injective means that the kernel of F is the 0 dimension. It's only 0. So the dimension of the kernel is 0. Therefore, the dimension of the image of F is same as dimension of V. Remember that image plus rank plus nullity theorem. This one is the most important thing. So the dimension of the kernel being 0 forces your dimension of the image to be same as the dimension of V. So the image must be V, because there is only one subspace of V of the same dimension as itself. So image is V, so F is surjective. So you told me F is injective, from there you concluded F is surjective, so F is bijective. On the other hand, you have told me G is surjective. Again use the same thing. G surjective means image of G is V. So dimension of image of G is dimension of V. Therefore the dimension of kernel is 0. Therefore the kernel of G is trivial. Therefore G is injective. So G surjective tells me G is injective. F injective tells me F is surjective. So both F and G are bijective. That's it. You don't even need that computation B1, B2, B1. Yes. Next.
Hey, sorry, sir.
Yes?
Seeing that we have load shedding and the videos will be a problem, what is the possibility of maybe putting the Word document on my UNISA, that we can follow you on written script, not so much the video, but obviously it will mean explanation in detail.
Well, I was thinking of putting up a separate video of this lecture containing all that I have said till now, but it will not have your interaction. Would that work? Hello?
Sir?
Yes?
How about maybe uploading examples of maybe this problem D of problem 4, D, E, F, so that maybe we can see how it's done?
No.
Oh, Costa.
No, you send me your queries and doubts. I will answer them, but you will come to the solution.
Oh. Hey.
You have immense power within you, don't belittle it. Don't belittle it. You have to work to get that power magnified. Don't belittle yourself. So you send your queries, I will send my support, and you will work through it. Next.
Sir?
Yes?
You know like when, okay, you know when we have like a zero vector?
Mm-hmm.
And then it's like open bracket T, close bracket. What does that mean?
Which one? Do you mean to say this one?
No, sir, it's like the zero vector and then it's open bracket T, close bracket. Like zero in, yeah.
Then?
Open bracket T, close bracket.
Open bracket?
T.
T.
Yes, but in brackets.
Okay.
Yes. What does that actually mean? Does it mean zero times T, or do they mean substitute zero as T as zero?
Where did you get this?
From the textbook.
Did I send it?
No, sir, it's from the textbook.
That would be difficult for me to say what is the convention followed in the textbook.
Do they mean that the
You could send me a scanned copy of that, and then I could revert back.
Yes, sir.
Okay. Any further questions?
Sorry, sir, you mentioned that you could upload lectures without our interaction because of the struggle with the load shedding?
Yes.
I think that might be quite helpful compared to trying to read what's on the board that you're writing now. I know we've had a lot of trouble trying to read the tops and bottoms and with the glare of the lights above it. It might be quite helpful.
Okay, I'll do so.
Thank you.
Sir, does this mean that we're not going to have interactive lectures anymore?
No, I didn't say so. I said for today.
Okay, sir.
Yeah. Any further questions? If not, we disperse.
Sir?
Yes.
They have a question here.
Bye. Yes.
My question is on the section on complement, where I'm having a problem with the complement.
On the section on?
Section on complement.
Oh, problem
Yes.
one.
Yes, because I need to understand a bit about this, sometimes you put a very large intersection. What does it mean? Does it mean there are several sets or what?
Do you mean to say something like this?
Yes.
Well, firstly I am saying that for I is a set. In my application, so I will be demanding I is non-empty. For each I, AI is also a set. Okay?
Yes.
And the collection of this, which I will write like this, is said to be a family of sets indexed by the set I. So now what does this mean? This is also a set. Remember, I said that whenever you tell me a set, I should be able to tell you whether an element is there or is not there. That means if I give you a formula or a property which describes when it should be there, it also tells you that the negation of that formula will tell you when it is not there. So I tell you, when is an element X a member of this set? This is true if and only if for all I from the set I, X is already a member of AI. So, it is a two-sided edge, you see. It tells you when does X belong to this index intersection, and on the other hand gives me a property. How to check? So I have to show that for each I, X is already in AI, and then it shall be in the intersection. Okay?
Yes. Yes. So in the family of sets, you just mentioned the family of sets, you don't talk about or you give examples.
No, definitely we had seen. Remember, when I wrote that the subspace, the set of all subspaces of R2, the zero space R2 itself, Lm where M is in R, and union the y-axis. So remember this one. So Lm, if I don't take R, all of them. So here is a indexed family of subspaces of R2 indexed by the rationals only.
Okay.
So there are many instances where we will be using this notion that there is a collection of sets, but these sets are indexed by some other set. So here it was indexed by Q, this family was indexed by Q. So it could be finite. You could also have where n is an irrational. So you have L root 2, L root 2 plus root 3, L root 3 and so on. All of them are there. Right? So, it's best therefore to work via this formula instead of seeing this always as a finite or the countable or any such thing like that.
Okay, sir, but then now when it comes to identifying the complement, that is what is the problem.
No, it is not. So you're trying to say that X, when will X not belong to this? Right? This is exactly saying that X is in the complement of this. Right? Now let's see. X is not here if this statement is false. And when can this statement be false? Everyone wears a red shirt. Everyone in the class wears a red shirt. When is this false?
When somebody's wearing a blue shirt.
Correct. So this is true if and only if there exists some I in I such that X doesn't belong to AI. Okay? But then you know that this means, this is exactly the definition of this. Remember, what is this set? X belongs to this if and only if there is some I in I such that X is in BI. Union means you're collecting them. It's a collection, it's a joining. So it's in the union means there is somewhere it is inside. Intersection means it's the commonalities. That's it. Is this clear now?
Yeah, it's getting better. I think that can check that problem is.
Which one?
Yeah, I was having problem with these things of complement.
Okay.
Thank you, sir.
Thank you. So it is verse now. Thanks.